Okay, so we're going to talk about electronics for the Internet of Things. And this might be a little boring, but it's really important. So we'll cover what an electronic signal is, what are the electricity's equations, GPIOs, PVM, ADC, and the difference between microcontrollers and computers. About signal processing, my colleague is going to discuss with you in the following days more, so it's going to be just a brief introduction to this. Okay, so first of all, what are electric signals? Does anyone in the room can know this? So what is an electric signal? What's a signal?
It's a waveform.
So it's a waveform, indeed.
Basically, what the electronic device sends to the processor.
Exactly. So what an electronic device sends to a processor? I think we can summarize that it's a stream of numbers that we have. So in electronics, we think at a signal as a stream of measurements. Okay. So basically, there's two types of signals, analog and digital. The thing is that everything in the environment is analog. So absolutely everything is actually continuous and analog. In order to use the information from the environment, we need digital signals. And basically, a digital signal is a stream of numbers. And it can be either 1 and 0, or it can have different values. So it's a misconception that actually analog signals, digital signals are only 1 and 0. Digital signals are any representation of a signal into the computer. Now the signal can be 1 and 0, or it can be a signal that has more numbers, more elements than 1 and 0. It's still digital because it's represented with 1 and 0s, but one sample of signal has more than a 1 and or a 0. So more bits. Okay, so basically there's two parameters for the signal. One is the number of bits per sample, and we're going to talk about what a sample means. And also we have the sampling rate, and we're going to talk about this as well. So here you have a sound wave. This would be the environmental thing. And here you have a sound wave in the digital world. So this is the sound wave that would be in reality, and this is how we see it in the digital world. You see it's in steps. So remember, in the environment, any function is continuous, but in the digital world or electronic world, there's a function with steps. If the steps are really, really small, then it seems like a continuous function, but in fact it's not. Okay, so bits per sample. The idea is that for recording a signal, we make measurements at a certain amount of time. Now, when we make a measurement, we have a number of bits where we can store, on which we can store that measurement. If we have 1 bit, then we can measure the signal, and we can say, okay, it's below half, then it's 0. If it's above half, it's 1. So basically, that's a really simple measurement. And this is usually what we call a digital signal. If we have more bits available, then we make the measurement. And for instance, if we have 2 bits available, we need to decide if the measurement is 0, 1, 2, or 3. Is it clear? The signal is not going to be a square one. It's going to be with steps, but only 4 steps possible. 4 steps are possible. If we have 3 bits, then we have 9 steps possible. Is it clear? So basically, this means the bits per sample. The better the hardware, the more bits per sample we have. And it becomes more expensive. Okay. What is the sampling? Sampling means making measurements. So basically, if we have a continuous signal over here, we will obtain something like this. And there's 2 things here. One is the number of bits per sample. So you see we have certain levels where we can categorize the signal. So when we make the measurement, we need to decide on a level from 0 to 2 to the power of n minus 1 where to put the value of the signal. Is it clear? the signal can have negative values. We still have a number of bits, but we can represent also negative numbers. But the number of symbols or different elements that the signal can be composed of is 2 to the power of n. Okay, so basically one thing is we will measure the signal at a certain point in time and we will put it on a certain level. This is the vertical line over here. The horizontal line in the square signal signifies the period of the sampling. So even if the signal is continuous, we can make measurements only at certain intervals in time. At certain moments in time, we will measure the signal. Between those intervals, between those times when we measure, the signal could have had any value. We did not measure it, so we do not know. So we will suppose it's either flat, either usually we will make a line between the 2 points. Is it clear? The faster we sample, the more accurate the signal. Is it clear? So remember, the digital signal has steps. The horizontal step is the period, and we will assume a value over there because we don't know it, we did not measure. The vertical value is due to the number of bits that we have. So if we have a device that can measure on 5 bits, there's only 32 different values for the signal. Yes? It can be either from 0 to 31, either something negative. It's our problem how to represent this, how to make a meaning out of the number of bits. But there's only 32 possible combinations. So regarding the sampling frequency, you can see on the graph, if we sample at a low frequency, that means at large intervals in time, the digital signal will not resemble the original signal, as you can see over here. So we have an input which is a sine wave. The output at a sampling rate which is low is going to be something that kind of is like a sine wave, but totally different. The faster we sample, the more accurate the signal, and the more expensive the hardware. So it's always a trade-off in sampling between the cost of the hardware and how accurate do we need the representation. Always 2 parameters which are important: the number of bits that the hardware can represent a value to, and the speed that it can measure. Is it clear? There's a little theorem called Nyquist's law or Nyquist theorem, and this states that you need to sample at least twice as fast as the highest frequency in the signal. And the proof is pretty complicated, and I'm going to give you the example of the phone. So human voice, if you use the human voice, it has frequency from 0.3 to 3.4 kilohertz. So it doesn't matter how fast or how loud we speak, our voice will translate into air vibrations, but it's never going to go higher than 3.4 kilohertz. Or it might, but we will not hear, because this is what we can hear. Is it clear? So basically, to make a phone, Nyquist's theorem says that we need to sample at least at 6.8 kilohertz. Do you know do you use Skype? What happens if internet connection is really bad? Besides breaking up. So one thing could be it breaks up. The second effect. Sometimes you can't hear the person, or you cannot understand what he says, or sometimes he has a really funny voice. Did this happen to somebody? Like having a baby voice or a really high voice? Nobody had this problem?
Yes, we have good internet.
Now you have good internet connection indeed, and Skype is getting better. But if you talk on the phone, sometimes it happens. So the guy has a really funny voice, or you cannot understand what he says, but you can understand he's talking, but you cannot understand what he says. This is due to the fact that the phone cannot send data at least 8 kilohertz. And if it can't do this, or it can't sample fast enough, it will not be able to reconstruct the original signal. Because we sample the signal when we speak, it gets sent over the network, it comes to your phone, and it's being reproduced by a speaker. But if it's not sampled fast enough, or at a higher accuracy, you cannot reproduce it. Is it clear? The proof is pretty complicated. You can ask Andrei, he can prove it in the following days. But this is something that you need to remember. So the bandwidth necessary is at least twice the sampling, at least twice the highest frequency in the signal. Is it clear? Any questions up to here? Okay. Electricity equations. Some of you might know these. Do you know Maxwell's equations? Those are differential equations. Those sum up perfectly the whole electricity domain. They all started with with Ohm's and Kirchhoff's equations. So this is enough for what we need. For higher frequency electronics, it's not, but for this it's absolutely sufficient. Ohm's law states that the current into a branch is equal to the voltage divided to the resistance of the branch. So this is basically Ohm's law. If we take this branch over here, we have 3 resistors. The current is equal to 3 volts. This is the voltage drop over the sum of the resistances. Please remember, currents are measured in amps, usually milliamps. So if you compute something and you come up with amps, that's really bad. It's going to fry boards immediately. So usually it's milliamps. Voltage is in volts, and resistance is in ohms. Okay, so is this clear for everybody? Please understand, whenever you have a resistance, you can draw a voltage drop on top of the resistor, and you will always compute that as equals to the current that flows through the resistors times the resistance. So this is one of the basic laws of electricity. Kirchhoff's first law states that in a node, and nodes are the small points in the schematics, so points where more than 2 branches meet, the currents going into the nodes are equal to the currents that go out of the nodes. It's like water. If you have more water pipes that go into a junction, the same amount of water needs to get out. It can be written also that the sum of the currents into a node is 0. And currents can be positive if the direction is outside the node, and negative if the direction is inside the node. Usually it doesn't matter, the sign of the current doesn't matter, the direction of the current doesn't matter, you can choose it however you like. As you see in my picture, I chose the currents to the right. If you put the current vice versa, you simply might get a negative value. So if you get a negative value for the current, the flowing direction is actually in the opposite sense. Is this clear? There was a joke. People had always discussed how to consider currents. Should they consider negative currents the ones that enter the node, or negative currents the ones that exit the node? And it always was a debate. And do you know how they had settled it? If you have an egg, a chicken egg, when the chicken goes outside of the egg, you cannot say it goes into the negative direction. So this is how they somehow established that currents that go out are positive and the ones that go in are negative. But it's a joke. Second Kirchhoff's law. This is related to loops. So loops are these ones, L1 and L2. The law states that the sum of the power sources into a loop is equal to the voltage, to the sum of the voltages drop into the loop. So the power, we have one single power source over here, which is E. So for loop number 1, we have E equals to the voltage drop over R1, and this is I1 times R1. So I1 flows in this direction. As it is the same direction with the source, with the power source, it's going to be considered positive. R1 is always positive. In the second loop, do we have any power sources? No. So their sum is 0. I2 is in, well, direction doesn't matter right now because we don't have a power source. So we will consider I2 positive. It goes through R1. And if we choose this direction of the loop, I3 is going to be opposite. So it's minus R3 times I1. Is it clear? So this is Kirchhoff's second law. Everything that we do this week is based on this. If you don't know this, you might fry boards. So please be careful. It always applies. Any questions? Let's talk about the voltage divider. This is really, really important. So if you understand this, you will understand how to connect sensors. If you do not understand this, you might have a hard time in understanding why we do certain connections in a certain way. So what is a voltage divider? I will rephrase. It splits the voltage. Yes, so basically, we have a battery. This is the ground, so the minus of the battery. This is the plus of the battery. Is this clear? We connect two resistors from the battery to the ground. Please understand that by resistors, we mean any device. So basically, any device can be somehow reduced to a resistor. So any sensor, any button, anything will be reduced to a resistor. So any consumer on the circuit is reduced to a resistor in DC. In AC, it's an impedance. So basically, we have two resistors. What you need to, and also we have a line which is V out. Yes, we will measure V out. How do we measure voltages? How? We use a voltage measurement device. Yes. Which is the what is the internal resistance of a voltage measurement device? How? Very high, basically infinite. Why? Because we want to measure, we do not want current to be drawn from the circuit into the measurement device. So we will need a very high resistance so that we can measure the voltage but do not impact the circuit. Is it clear? So whenever we have a measurement, we can assume that this resistance from V out to the ground is infinite. And it's very important. We will assume there is no current flowing over here. So basically the current that comes from V in goes through R1 and splits towards V out and towards the ground. Is it true? Now, if we consider that V out has an infinite resistance, no current is going to flow that way. So we will assume for the voltage divider that the whole current goes through R1 and then goes through R2. Is this clear? So whenever we have a measurement, the branch that is actually measuring will have no current. So let's see. V1, we will consider V1 the voltage from V in up to the middle, and V2 from the middle to the ground. Ohm's law says it's I times R1, and V2 is the same with V out. As we said, there's no current here. and this is the same node basically, is equal to I R2. Is this correct? Is it clear for everybody? So this is one of the main things that you need to understand. So let's see, what happens if R1 is 0? How much is V out? It's equal to V in. Is this correct? Let's see, if R2 is 0, how much is V out? 0. Why? Either you apply Ohm's law, either you can see it's connected to the ground. What does it mean, R2 being 0? Technically speaking, there's no resistance, there's a cable. So any cable or a short circuit has 0 resistance. If R2 is infinite, what happens? V out is V in. Is this clear for everybody? What does it mean, an infinite resistor? No current passes, meaning, in technically speaking, it is an open circuit. So basically, there's no cable. Those points are not connected. So basically, if R2 is infinite, V out is connected to V in via R1. So basically, what we measure is something very close to V in. If we consider it infinite, completely infinite, we know the voltage V in is fixed, so this voltage here is infinitely greater than the voltage here. Basically, we will measure almost V in. So there's going to be a small voltage drop, most probably not sensible by the device. So what happens if R1 and R2 are 0? Short circuit. So careful to this. Never ever, when you design a circuit, please be careful that in no way, under no circumstances, V in will be connected directly to the ground. This means when I press a button, there's no way that I can connect V in to the ground. Is it clear? So never ever, always one of these resistances needs to exist. Is it clear? Just to give you an example, if we have a button can be modeled as a resistance. If the button is not pressed, what is the resistance? Infinite. If it's pressed, it's 0. So please be careful when you put buttons. When you press the button, its resistance becomes 0. So watch out not to connect some VCC directly to the ground. Okay? Boards might smoke. So now that we have discussed the electronics part, let's discuss about GPIO. So this is the part where I'm going to explain how to use the boards and how to use the electronic components on the boards. GPIO means general purpose input-output. It makes use of these pins. So embedded boards are like computers. The main difference is that they expose some electronic pins for you to control. Pins can be controlled either with GPIO, general purpose input-output, which usually means digital signals, 1 and 0 signals. They can either measure voltage, that's an analog input signal. They can either make PWM, and we're going to discuss this a little bit later. For now, general purpose input-output. So values that you can set or get for general purpose input-output are low and high, usually 0 and 1 into programming. There's two ways that GPIO pins can act. Either as an output, and then they act exactly like a battery. Either as an input, and then they act like a measuring device, like a voltage measuring device. For the output, I have the example of the Raspberry Pi. This pin over here is black, and it's the ground. This can be considered the minus of the battery. This pin over here, the green one, which is connected to the resistor, is going to be the plus of the battery. The ground cannot be controlled. So pins which are marked on boards with ground, have always a voltage of 0, and that cannot be changed. Pins that allow GPIO can either generate a 0 voltage, which is identical to the ground, either generate a positive voltage, which is usually either 5, either 3.3, either 1.8. It depends on the board's construction. For the Raspberry Pi it's 3.3, for Arduino it's 5, for Intel Galileo and Edison it's 5. Actually for Edison the expansion board is 5. The board is actually 1.8. My example over here, so we have a LED which is connected to the ground, connected via a resistor to the pin. The pin is marked as output, so when I can write values on the pin. If I will write, the value 0, what is going to be the output? Sorry? So if I'm going to write 0, if I'm going to write 0 on this pin, the voltage here is 0, the voltage here will be 0. What happens with the LED? Stays off, yes? If I'm writing 1 on this pin, what is going to be the voltage? It's 3.3, it's the Raspberry Pi. The LED lights up. Is it clear? Question, what is this resistance? It keeps the LED from popping, but is this clear for everybody or no? So LEDs have LEDs are diodes. Diodes have infinite resistance up to 0.6 volts. Above, they drop to 0 immediately. So LEDs, in contrast with light bulbs, which have internal resistance, have no internal resistance. So the LED's resistance is 0. If there's no resistor on the way, it will simply pop. And the board might also fry. It's a short circuit. Intel Galileo sometimes smokes. The chip heats up. For the Raspberry Pi, it stops. I think Edison is also stopping. But just to be safe, please understand, LEDs are packaged with a resistance. Always when you use a LED, just put a resistance. Okay, what happens if we would connect this pin to the power supply and this pin to pin number 12? So what happens if we connect the positive part of the LED to 3.3 and the negative part of the LED to a GPIO pin? So let's see. If the GPIO pin, yes? It depends on the value of the GPIO. Indeed. So, if the positive leg of the pin, of the LED, is connected to 3.3, that's the VCC of the board, and the negative leg of the pin is connected to a GPIO, the effect is vice versa. If the GPIO is 1, we have 3.3 volts to the positive leg and 3.3 volts to the negative LED. It will not light, it will stay off. Because there's no difference of 0.6 between the pins. There's no difference of voltage, exactly. If we put 0 on the GPIO pin, it acts like the minus of a battery. The LED gets a voltage from the 3.3 that flows to the ground via the GPIO pin. Is it clear? So please understand that you can either control the minus of the battery or the plus of the battery with the GPIO pin. It's very important to look at the schematics when you have a device and see how the LED was connected. So in no way writing 1 on a pin will mean lighting up a LED, or writing 0 on a pin will mean putting a LED off. Inputs. Inputs are voltage dividers. Actually, are using voltage dividers. This is the V out is the input of the board. So the V out of a voltage divider will be connected to an input pin on the device, on our device. Input pins always measure voltage. GPIO pins, so as I said, GPIO pins measure voltage. So always when you have to connect something that you need to measure, if the device has only 2 legs, you need to you need to replace one of the resistances in the voltage divider with the device. Most of the sensors which are a little more advanced will have 3 legs. The VCC or the V-in, the ground, and the signal leg. It's because internally they have the voltage divider. So if the sensor is really simple, just replace one of the resistances and understand what you measure. If the sensor is more advanced, it will have 3 legs. Some have more, but we're talking about simple sensors. So, question is, if it's a voltage measurement, how many bits does it use? If it's a GPIO pin, how many bits? 1. So, it's a measuring device, but a really simple one, which measures 1 bit. Actually, it looks if it's below half or above half. And that's all that it can give you. So you can read a value of 0 or a value of 1, but not more. This is GPIO. Do you have any questions here? PWM, or pulse width modulation. It's very, very important to understand that this is not an analog signal. Most of the programming libraries describe PWM as analog output, which is somehow wrong. PWM, pulse width modulation, is generating signals like this. So basically, pins that are capable of PWM are capable of generating quadratic periodic signals. Signals like these ones over here. PWM comes from the duty cycle of the pulse, meaning how much of the period of the signal is 1, how much of the period of the signal is 0. That's the pulse width over here. So let's take an example. So usually PWM signals are controlled with a number from 0 to 255 on the boards that we use. Depending on the hardware, this can be higher. If we ask for a signal of 0, so PWM signal with 0, it will generate a line at 0. This is the same as a GPIO pin writing low. So it will generate a periodic signal, as you can see, but the period of time that the signal has to be 1 is 0. So basically the signal is never 1. Is it clear? If we go to the maximum, 255, signal has to be 1 the whole period. So this is the equivalent of GPIO making 1. And in between, it depends. So for instance, if we have a 25 duty cycle, as you can see, 25% of the time, the signal is going to be 1, the rest is going to be 0. 50, it's 50%, 75 is 75%. Is this clear? This is really fast. So periods go to, frequencies go up to 200 kilohertz and can go even higher. Analog to digital converters. Have we seen one until now?
Our phone, for example.
Sorry?
Our
So you have the phone. The phone is an analog to digital converter. When you speak, the microphone on the phone is an analog to digital converter. But in my presentation, did we discuss about an analog to digital converter? No, that was the slide with the red lines and the sine form. But talking about the pins, did we see an analog to digital converter until now? We did. You know, the GPIO input pin is a 1-bit analog to digital converter. It takes an analog signal, measures it, and decides on 1 bit if it's below half or above half. So basically, we have an analog to digital signal. An analog to digital converter has 2 parameters. Has more, but 2 important ones: number of bits per sample and the sampling rate. So how fast it is, how many different levels it does recognize. So if you have 1 bit, for 1 bit, an ADC on 1 bit is what actually? It's a GPIO input. So a 1-bit ADC is always a GPIO input. If we have n bits, an ADC, or analog to digital converter, of n bits, how many values do we have? How many different values can we have? 2 to the power of n, yes? So it's from 0 to 2 to the power of n minus 1. Well, it depends how we interpret the value. Okay. Now, this is the board that we are going to use in this summer school. As you can see, it has 6 pins which are numbered with A0 to A5, which can read analog values. This does not mean it has 6 ADCs on the board. ADCs are expensive. The more bits they have, the higher speed, higher sampling rate they have, the more expensive they are, and they're really expensive. So basically what they do on these boards, they have 1 ADC and they multiplex it. So basically there's a controller, a hardware controller, which reads a value on the ADC. So no, connects the ADC to A0, reads the value, reports it back. Connects the ADC to A1, reads the value, reports it back. A2, A3, the same. It goes up to A5, then connects it back to A0. Is this clear? So on boards like Intel Edison, you have the sampling rate, which is the speed of the ADC, plus the multiplexing speed. So when you see that Intel Edison or some board has an ADC of a certain speed, please look if it's multiplexed. Because if it's multiplexed, you will read n times slower. In this case, 6 times slower. Because it needs to sample every pin, one pin at a time. Is this clear? Yes? The question is if you can set it to read only 1 point. It depends on the hardware. For Intel Edison, I don't know. I think for Arduino, you can't. So it really depends on the hardware implementation. The cheaper the board, the higher the probability that you can't. But I don't know for Intel Edison. We can check. But this is important, so you really need to understand this. Intel Edison usually has 12 bits ADCs, and the Arduino has 10 bits ADCs. Do you know Raspberry Pi? Raspberry Pi has no ADC. It's no ADC whatsoever. This is the serious problem on the Raspberry Pi. This is why you usually need to connect some microcontroller to it, because the Raspberry Pi was designed without any ADC. And when it comes to PWM, Intel Edison has a PWM. Raspberry Pi has a software PWM. It's built into the driver, but it's not stable, so it's hard to use. Regarding Intel Edison, Edison is the small chip over here. So please be aware that this chip over here has no ADC. So if you buy an Intel Edison, you might have the surprise that this board has no ADC and you cannot connect analog sensors. The board that we are using is the expansion board for the Edison, and the ADC is located on this board. So just keep in mind when buying hardware, please double check that the device actually has ADCs if you need it. Okay, so we're getting to the last point of our presentation today. it's about microcontrollers versus computers. When we started marketing Wyliodrin, the cloud solution that we did, we went to several universities and educational institutions, and the answer that we got was, we have Arduino, why do we need the internet connected boards and computers and so on? Well, they're not the same. So there's a big difference between microcontrollers, as the Arduino over here, microcontroller boards, and computer boards, like the Raspberry Pi over here, also called embedded systems. And we'll take the first one. So microcontrollers are really low power processing units. They process at low speeds, like Arduino has something about 16 megahertz. Low memory, Arduino has 2 kilobytes of memory and 32 kilobytes for program memory. But they consume very, very little, so they can work on battery a lot. They are excellent for controlling hardware. So they have GPIO, they have PWMs, they have ADCs, and they are real time. So the only program that is running on a microcontroller is the program that you wrote, in most of the cases. That means that you know exactly when something is going to be executed. Or you can estimate with a really good accuracy. On the other hand, we have embedded boards, which are computers. These are full power computers, so meaning they have a full-blown operating system, they have 900 to 1 gigahertz in speed, they have a high amount of RAM, like 1 gigabyte. They are really modest in controlling hardware. So they have GPIO, and in most of the cases they have some kind of expansion on the board that knows either PWM, either some ADC. No way the board is real time. Your program is one of the many programs that the operating system runs, plus you have an operating system that needs to run drivers. So you cannot predict when something is going to be executed. There's no way to have a fixed delay, so you cannot sample some data with a very clear delay. The best that we could do was tens of milliseconds, while on microcontrollers you can do it with a precision of tens of nanoseconds. Is it clear? So microcontrollers are really good in controlling hardware, while computers, like embedded boards, are really good in processing. So the combination of the two is the solution. Just to give you a bigger picture, any device that you have is going to have some microcontroller and the CPU. If you look inside your computers, every peripheral, from the hard drive, the CD-ROM, the USB hub, the networking card, they have microcontrollers embedded in them. And the microcontroller communicates with the CPU in your computer. By no means the CPU on your computer is controlling your hard drive. Is this clear? Going to electronics. In most of the cases, you will have an embedded device which is going to process, and you will connect sensors to it. Sensors and peripherals. As the device is really bad in talking directly to hardware, you will need some kind of microcontroller on the way. And usually, sensors, which are more expensive, come with the microcontroller inside. If you use Arduino to connect some sensors to the Raspberry Pi, for instance, you are actually building a more intelligent sensor with the Arduino, which you connect then to the Raspberry Pi. Is this clear? So please understand that we are talking about firmware when we talk about microcontrollers, and we talk about software when we talk about computers. So from now on, we will refer as firmware to the programs that we write for microcontrollers, and software for the programs that we write for computers. Is this clear? Okay, a few words about Intel Edison, which we will use during this summer school. It has a CPU and the microcontroller. The microcontroller is still not available for programmers. Intel is working on this, and hopefully they will release something. So it has some firmware. You will be able to write it, but not at the moment. For now, we can write only software. The good part is that it has GPIOs. It has hardware PWM because it has an extension and a driver in the system that can control the extension for PWM, and it has an ADC on the expansion board. So you can do most of the things that you do with a microcontroller. The only thing that's lacking from Edison is real time. So sampling is not going to be real time. Okay, if you have any questions.